Do some measurement techniques now that you know how to use all these instruments. So in most of these test instruments, there's two main factors, resolution and accuracy. Just because you have high resolution doesn't mean it's accurate. I mean, if you think of a Harbor Freight tape measure, and it might be graduated in 64ths of an inch, but it's probably only accurate to a 16th or an eighth of an inch. So test instruments are the same way. You have to look at what the accuracy is and then what the resolution is. And the resolution just means the minimum value that you can detect or display for a signal, where the accuracy is, I guess, the percentage between what it should be and what it's actually showing. So some standard relative to the measurement that you have. So in the frequency counter, okay, the main thing is the time base and how accurate that is. If you had a time base of 1 part per million, in this little example down here, if you were measuring a signal in 2 meter band of 146.520, it means that it could be off by 146.5 hertz either way. So which of the following factors most affects the accuracy of a frequency counter? Time-based accuracy. In the case of a voltmeter or multimeter, they have, or they, at least they used to on the older ones, express the ohms per volt rating for it. And that would tell you what the impedance was. So you multiply the full scale volts times the ohms per volt, and you actually get the impedance rating on that particular scale. Now with most of the multimeters, they have a field effect transistor front end, so it has an extremely high impedance front end, so it isn't really much of an issue anymore. You're looking at multi-mega ohms as far as input impedance. Where with an older analog type like we used to use, it could load down the circuit. Huh?
You shot one. My son, he got it last year. He was on the shit. Why don't you do?
Actually, the Harbor Freight ones aren't bad.
Really?
For the money, but and you can get some pretty decent ones for 20-30 bucks. I mean, if you want a really good one, you're talking several hundred.
Yeah, the Flip 289 is around 800 bucks.
What is the significance of voltmeter sensitivity expressed in ohms per volt? Can you get rid of any?
I'll get rid of all of them.
Well, let's try delta. How about that? Full scale reading in amps divided by that. How about Charlie? Anybody got alpha?
Yeah, it wouldn't be either. It's enough power.
So for each range, you multiply the ohms per volt. Because each, and in most cases, they'll have different ranges unless you got one of the digital ones which does auto ranging and you don't have to pick.
The key is the word impedance, right? So, because that's going to affect circuit.
Right.
Your, everything else is
Right.
power and voltage and
Right.
chunks and
And they came out with vacuum tube voltmeters to solve that problem, which acted like a FET front end. It's a very high impedance front end.
I have an RCA one. I actually have two RCA ones that need to be refurbed, but
Yeah, I have an old one somewhere. It has a nice big meter on it.
yes, yeah, the meter was large, so.
But you know, it's this big.
Yeah,
With a handle.
right.
Measure the forward and reflected power. You use that with a directional watt meter or an SWR bridge. And basically, it's going to show how much power is actually being delivered to the load versus how much is being reflected back because of an impedance mismatch. So if you we're measuring 100 watts forward power, but you're seeing 25 watts reflected power back, it means that only 75 watts was actually going to the load or the antenna, whatever you're driving. And that 25 watts is reflected back. And of course, then it's going to get reflected back again, and so on and so forth until it's totally dissipated, because on every trip, you're going to have some loss in the transmission line. So when it comes back, you lose some and it goes back again. And eventually, and every time it does get reflected, it does add a little more power to the antenna. So you don't actually lose all of that 25 watts. Some of it is actually gained by every little trip it makes before it's totally absorbed. And for Vanessa, there's the formula to calculate SWR.
Okay.
How much power is being absorbed by the load when a directional power meter connected between a transmitter and a terminating load reads 100 watts forward power and 25 watts reflected power? Okay. That was a hard one. Did you have to calculate that?
Yeah, I was on that. Didn't.
Q, okay. Sometimes we want to know the Q factor or quality factor of the circuit. In case of resonant circuits, antennas, the higher the Q, the narrower the bandwidth. So if you know if you can measure the bandwidth by looking at it on a frequency plot, you can figure out what the Q is for that circuit. So you look for the two upper and lower cutoff points, or half dB points, and that's where you measure the half power bandwidth, and that determines the Q. Which of the following can be used to measure the Q of a series tuned circuit? Oh, intermodulation distortion. This is normally measured with what they call a two-tone test. And they take two audio tones that are not harmonically related. Means one's not a multiple of another. Usually they use the 700 hertz and 1900 hertz as the two audio signals. And they modulate a carrier with that. And then look at the frequency spectrum on your spectrum analyzer and see whether or not you actually see the carrier and those two other signals, sidebands. If there's intermodulation distortion, you're going to have additional frequency components. Which of the following methods measures intermodulation distortion in an SSB transmitter? So you can throw two out. Which two?
You can see with the, sorry, Delta, you throw out.
So alpha,
Well, if you throw out Charlie, Delta, and Alpha, that only leaves Bravo.
That's true.
Because we said it was used two audio frequency signals. So it can't be Alpha or Delta. That IMD will come up again. So kind of remember the concept. We didn't talk about, we talked about antenna analyzer, but not a vector network analyzer. Can measure a lot more things. Input impedance, output impedance, because you can look, they have two ports so that you can hook it up to a network like a filter, for instance, and measure insertion loss through it or frequency response, phase changes, all this kind of stuff. The reflection coefficient, it'll measure SWR just like an antenna analyzer. You have to calibrate them in order to do it. And you do that by using, you connect a short circuit to it and calibrate it. You connect an open circuit and calibrate it. And then you do a load, which is typically 50 ohms, and calibrate it. And all you're really doing is, you remember on the Smith chart, you're doing those 3 points. The 0 point, the 1, which is normalized to 50, and then the open, which is infinity. And they actually do, in most cases, present you, one of the options is to see a Smith chart display. So you can see the change in impedance and reactance with frequency on the plot. And where it crosses the axis is where it's going to be resonant. Which of the following can be measured with a vector network analyzer?
delta,
Which of the following can be measured by a two-port vector network analyzer?
oh,
Because you're feeding a signal in and then looking at the output of it. Because it actually has a signal generator in it, and it produces about a 10 milliwatt output signal. What 3 test loads are used to calibrate an RF vector network analyzer? They use what's called S parameters, scatter parameters. I'm not sure where the scatter came from. And they're defined as S11, S12, S21, and S22. Normally, you only need to, so the stuff we're talking about, S21 and S11, where the first number is the input, so it's looking at port 2, and your output or signal from the device is on port 1. So an S21 would allow you to measure the gain or loss of a circuit. If it's an S11, it means that you're outputting or you're looking at port 1 as an input. You're also using port 1 as an output. So what you're seeing is the reflection. You're sending a signal out, you're looking at the reflection coming back. So it's just like a directional watt meter. It's looking at forward and reverse. And that's how you measure SWR. The other combinations are used to do other things, which is more advanced than extra. This is kind of what's inside one of these things. And when you're doing the 2-port test, your device under test is connected between port 1 and port 2. And depending on what mode you set up in it, where you're going to, which S parameter you're going to look at, whether you're doing a 1-1 or a 2-1. They're pretty nifty little devices, but it takes a little bit to learn how to use it because of the menu system. It's, invented by the Chinese. Actually, I don't think they copied it from somebody. I think somebody over there actually did it. What do the subscripts of S parameters represent? This means ports, port 1 and port 2. What S parameter is equivalent to forward gain? Charlie. Look at the outputs, put the signal on the input. Which S parameters represent input port return loss or reflection coefficient equivalent to voltage standing wave ratio? Alpha. Wasn't that easy?